Hello and welcome to another video for Calculus 1. In this video, we are going to discuss about fundamental theorem of calculus. So there are two parts for the fundamental theorem of calculus. The first one is part 1, which we are going to discuss right now, and then we'll see the other one next. So this one says if f is a continuous function on AB, closed interval AB, and then the area function A defined by, so this is the definition of the area function, which is given by the integral from a to x of f of t dt on that interval, closed interval AB, is continuous on AB and differentiable on open interval AB, and the derivative of the area function a prime of x equals f of x. So this is very important. And equivalently, this can be written as a prime of x, or the derivative of the area function, equals the derivative of the integral from a to x of f of t dt, or which is simply the function f of x. So this seems kind of a little bit complicated when you just see that definition or that theorem. So let's illustrate this in an example. Okay, so I'll give you an example just to illustrate this one, and that probably helps you to understand what the theorem is talking about. So let's go ahead and consider a function. Okay, so let's say f of t equals 2t plus 2. I'm just considering random function. Now, based off that theorem, this theorem is saying the area function a of x is given by the integration from, let's say we are going to find the area from 1. So let's say that a is 1, and then we go all the way to x, okay? And then f of t dt, okay? So now let's stop here and let's go ahead and graph this function, the one that we just considered, okay? So let me go ahead and draw the axis. So this is y-axis, this is x-axis. Okay, so here we have function f of t equals 2t plus t. So I'm going to say this is t, this is f of t, okay? And then our function is 2t plus 2. So it's a straight line. Let's say that's our function. So this is 2. So we want to find the area from 1 all the way to some x. So we don't know what that x is. Okay, it could be any number. So now, if we just complete this area, so this is the area that we are looking at. Okay, so this is the region, this is the area that we are trying to find. Now let's find a function that represents this area. So that's what we are going to do next. So now if you look over there, so we have this trapezoid. So the length of this side is, if you plug in, so this is the function f of t equals 2t plus 2. So if you plug in 1 here, we get 4. That's this height here. And then this one right here, this is, if I plug in x, I just get 2x plus 2. So that's the length of this side. Now we know that the area of a trapezoid is, let's say, area equals 1/2 times height. So this is the height of the trapezoid here, which is x minus 1, times the sum of the parallel sides. So the parallel sides are 4 plus 2x plus 2. So 4 is this side plus 2x plus 2 is the other side. Now if we simplify this, so I'm not going to do all of the simplification, but if you distribute, multiply, this is what we are going to get at the end. We'll get x squared plus 2x minus 3. So that is the area function. Now what does this say is, for example, if you want to find the area from 1 to, let's say, 2, you can just replace x with 2. So the area from, so area of this region from 1 to, let's say, 2 is given by a of 2. So you can just plug it in here, you get the number, and that gives the area. So that's what that area function is. It's a function that gives the area, okay? Now, what is this fundamental theorem of calculus is saying is, now if we find the derivative of this area function, okay, so if we find the derivative of the area function, this one, we must get the original function right here. So let's check that if that works. So if I go ahead and find a prime of x, then we get 2x plus 2. That's what we have here, 2t plus 2. So this is same as f of x. So if I replace t with x, then I get this one. So that's what this theorem is saying here. The area derivative of the area function is f of x. Or if we take this one and if we integrate that from a to x, we will get the area function. So if we integrate this function 2t plus 2 from 1 to x dt, that's going to give us x squared plus 2x minus 3. That's another way to interpret this. So that's the meaning of this one. Okay, so if we have an area function, if we find the derivative of the area function, then that derivative will give us the function representing the curve. So now, what we are going to do here is we are going to look at a couple of examples where we are going to find the derivative of the integral. So this is the derivative of this integral, which is the derivative of the area function. So that's what we are going to do in next few examples. So use part one. So let's look at the first example. Use part one of the fundamental theorem of calculus to find the derivative of this function. So the derivative of this integral, so d over dx of this one, so which is 1 to x cosine squared t dt equals, so if you look back here, that equals just f of x. Or what we do is we'll just replace t with x. So this is just cosine squared x. Okay. Now similarly, let's look at the second example here. So the derivative of this integral from x to 6 of 3 plus square root of t dt equals, so that equals, so we just replace t with x, but in this case, so just be careful. Our theorem says a constant to the x, but here we have x to the 16. So we are going to use one of the properties of the integral. So if we switch that limit, it becomes negative. So this is going to become, so let me rewrite this here. So this is same as saying negative. So we'll pull that negative out. So d over dx, okay, of 16. This is 16 to x 3 plus square root of t dt. Now we can use the fundamental theorem of calculus, and then this becomes 3 plus square root of x. Okay, so we have that negative sign because we switched the limit. Now let's look at this example here. Again, very similar. So d over dx, so we are finding the derivative of this integral from 1 to square root of x t squared over t squared plus 1 dt, and that becomes, there's something wrong with this pen, so that equals, okay, so now what we do here is we'll replace t with square root of x, so this becomes square root of x squared over square root of x squared plus 1. Now one thing we really need to be careful, if you go back to our fundamental theorem statement here, when we have a to x, that's the derivative, okay? But now here we have a to square root of x, so which means we have to use the chain rule here. So we need to find the derivative of square root of x, which is 1/2 x to the negative 1/2. And we'll go ahead and simplify this. So this becomes x over x plus 1 times, so this becomes 1 over 2 square root of x. And then if we simplify this, we will get square root of x over 2 times x plus 1. Okay, so similarly, let's go ahead and find this derivative of this integral. So d over dx of 0 to x cubed sine t squared dt equals, so what we are going to do is we are going to replace t with x cubed, so this becomes sine x cubed x cubed squared, and then times the x. So we need to find the derivative of x cubed, which is 3x squared. And then we can rewrite this as 3x squared sine x to the sixth. So that was the first part of the fundamental theorem of calculus. The second part of fundamental theorem of calculus is very important, and this is what we were looking for quite a few weeks because we were trying to find the exact area, the true area under the curve, or the net area under the curve. And this is what's going to give us the exact or the true area under the curve. So for example, we have a function f of x. Okay, let me draw the graph here. So let's say this is f of x, and we are interested in finding the area from A to B. Okay, so we are interested in finding this area. Now, what this theorem says is this area, we already looked at this one when we did the definite integral. So this area is given by the integral from A to B f of x dx. That we already know that. Okay. Now, this fundamental theorem of calculus says that these definite integral equals the entire derivative of this function, which is represented by uppercase f of x, evaluated at b minus a, which we represent as a to b. Or this is same as saying f of b, so this is the entire derivative of the function f minus f of a. So basically what we do is we'll find the entire derivative of this function, and then we'll evaluate that function on this upper limit. So we'll get a value that is f of b. Again, we evaluate that entire derivative at the lower function, lower limit, which is f of a, and then we subtract that. And that gives us the net area under the curve, or this area under the curve, or that is the value of the definite integral. So we're going to look at a couple of examples to illustrate that. Okay, so notation here, this just means when we write this, it just means f of b minus f of a. So we write that one, and then we write f of b minus f of a. Okay, so let's go ahead and look at some examples. So the first example here, we are going to evaluate this definite integral. So what we do is we'll first find the entire derivative. Okay, so in order to do that, what we're going to do is let's rewrite this function as a instead of that rational function, we'll put that in the numerator, and we'll write it x to the negative third dx. Now the entire derivative of x to the negative third is x, so if we have x to the n, the entire derivative is x to the n plus 1 over n plus 1. So negative 3 plus 1 is negative 2 over negative 2, and then we go from 1 to 2. So that's the notation. So as soon as we do find the entire derivative, we are not going to write that integral symbol. Okay, so we'll change it to that form. So now this just means, so let's, before we plug those numbers in, let's go ahead and simplify this. This just means negative 1 over 2 x squared. And we go from 1 to 2. Now this becomes, so we plug in 2, so negative 1 over 2 times 2 squared, that is f of b. If you think about that fundamental theorem of calculus, so that's f of b minus f of a, means we plug in 1. So minus, again, there's a negative 1 over 2 times 1 squared. And then we'll just evaluate that. You can either put it into the calculator, or we can do this by hand. So this becomes, the first one becomes negative 1 over 8. And then we have minus 1 over 2. So negative 1 over 2. So this becomes negative 1 over 8 plus 1 over 2, and which is 3/8. So that is the definite integral, okay, value of the definite integral, or in another word, that is the area under this curve, the net area under this curve from 1 to 2. Another way to interpret that, okay? So now let's look at the second example that we have here. Again, it's the same process. So we're going to find the antiderivative. So antiderivative of 6x squared is 6x cubed over 3 minus 8x squared over 2 plus 5x, and then we go from 1 to 2. Let's simplify before we plug the numbers in. So this is 2x cubed minus 8x squared over 2 means 4x squared plus 5x, and we go from 1 to 2. So let's go ahead and plug in 2 first. So when we plug in 2, so we're going to take that 2, and we'll plug it in here, here, and here. So when we plug in 2, we get 2 cubed is 8 times 2 is 16, minus 2 squared is 4 times 4 is 16, plus 2 times 5 is 10. That is f of b. Then minus, make sure that you put the parentheses so that you don't make a mistake. Okay, so f of b minus f of a means we plug in 1. So 1 cubed is 1 times 2 is 2. Then that is minus 4 plus 5. And then we get 10 minus, so here we get 5 minus 4 is 1 plus 2 is 3. And the final answer is 7. Let's look at more examples. So here, in order to find the antiderivative first, what we do is we'll split this fraction into two fractions. Okay, so 1 to 2, and then I'm going to write x to the fifth over x to the fourth minus x squared over x to the fourth dx. And then we can write this as 1 to 2. So this is x minus, we can write it as x to the negative 2. Okay, so now what we're going to do next is we're going to go ahead and find the antiderivative. So the antiderivative of x is x squared over 2 minus antiderivative of x to the negative 2 is x to the negative 1, because we do negative 2 plus 1, and then negative 1 here in the bottom, and I go from 1 to 2. So this is same as writing x squared over 2 minus, that becomes plus actually because we have negative and negative, it's 1 over x. We go from 1 to 2. Now when we plug in 2, so 2 squared is 4 over 2 is 2 plus 1 over 2 minus, when I plug in 1, I get 1 over 2 plus 1 over 1 is just 1. And then when we combine these two fractions, so it is 2 plus 1 half minus 1 half minus 1. So 1 half and 1 half goes away. Then I have 2 minus 1, which is just 1. So this equals 1. Now let's do the next example that we have here. First, we are going to find the antiderivative of 7 times e to the x, which is just 7 times e to the x. And then we go from natural log of 2 to natural log of 5. Okay. Now, when I plug in natural log of 5, that becomes ln 5 here in the exponent, and then minus 7 e to the ln 2. So we know that if we have e to the ln of x, and that is just x, or in log, you have learned this one. Okay, so if we have a base a, then log base a of x, if they match, then that is just x. So here e and ln, it has a base of e, so they match, so it's just x. Okay, so similarly here, what we have is this one here is just 5, and this is just 2. So we can rewrite this as 7 times 5 minus 7 times 2, which is 35 minus 14, and we get 21. Here's another example. Sorry, we should have a parenthesis here. Now, this equals, again, first we are going to go ahead and find the antiderivative. So the antiderivative of cosine theta is sine theta, and it's not negative. The derivative is negative. But the antiderivative of sine theta is negative cosine theta. So this is negative 3 cosine theta, and we go from 0 to pi. So let's go ahead and plug in pi first. So sine pi minus 3 cosine pi. So that is f of b minus f of a means sine 0 minus 3 cosine 0. Now sine pi is 0 minus 3 cosine pi is negative 1. minus sine 0 is 0, minus 3 times cosine 0 is 1. So we get, here we get 3, minus here we get negative 3, which gives us 3 plus 3, and that is 6. Now let's look at one more example. Here again, we are going to split this fraction before we find the antiderivative. So let's go ahead and do that. So integral from 1 over 25 to 1 over 9. And then if we split this fraction, so we are going to get x to the 1 half divided by x. Square root of x means x to the 1 half divided by this x minus 1 over x dx. Okay, now let's go ahead and simplify this. So 1/25 over 1/9. So this is x to the negative 1 half minus, let's leave this as 1 over x because the antiderivative of 1 over x is natural log of x. So we can just write that like that. Okay, so now the antiderivative of x to the negative 1 half is we add 1, which is 1 half, and we divide by 1 half. So this is x to the 1 half divided by 1 half minus natural log of x. And we go from 1/25 to 1/9. Okay, now we get, so this can be, the first one can be written as dividing by 1 half is same as multiplying by 2. Then x to the 1 half is just the square root of x minus natural log of x, and we go from 1 over 25 to 1 over 9. So we have to do a lot of algebra here, so be patient and let's keep going on. Okay, so now we are going to find f of b minus f of a. So that means I'll plug in 1/9 first. So 2 times the square root of 1/9 minus natural log of 1/9, that is f of b, minus f of a is 2 square root of 1 over 25 minus natural log of 1 over 25. That's what we have. Now let me write this up here. Okay, so this one from here, this equals, so the first one is 2 times square root of 1/9 is 2 times 1/3 minus, so you have learned in algebra that any log, okay, log base a of x over y can be written as log base a of x minus log base a of y. So if you have a division, this is the quotient rule, okay, so if you are dividing, then that can be changed as a difference. So that's what we are going to do here. So we have natural log of 1/9, so we can write it as natural log of 1 minus natural log of 9. And that is the first part, minus. We'll do the same thing for the second part. So this is 2 times 1/5. Then minus, so we have natural log of 1 minus natural log of 25. Okay, now this becomes 2/3. So now natural log of 1 is 0. So we have negative natural log of 9 here. When you distribute that negative, that becomes plus natural log of 9. And then we have minus, this is 2/5 minus, again this is 0, so we have plus natural log of 25. Now let's open this parenthesis, so we get 2/3 plus natural log of 9 minus 2/5 minus natural log of 25. So now what we can do is we can combine these two numbers, and then we can combine the log. So we can combine natural log of 9 and minus natural log of 25. So this one becomes, so 2/3 minus 2/5, you can do the math. So 2/3 minus 2/5 is 4 over 15 plus, so natural log of 9 minus natural log of 25. We are going to use the same rule that we used earlier. So now we are going to combine these two, which gives us natural log of 9 over 25. So this is natural log of 9 over 25. So for the exact answer, we can just leave it right here. But if you want to approximate an answer, then you can put this into the calculator and you should get approximately, this is negative 0.75498, okay? So we'll just stop here for this video. I'll see you again in the next video.